2025 could be an explosive year for researchers at Oregon State University. They're predicting an undersea volcano called Axial Seamount will erupt sometime this year.
The axial seamount has emerged in early 2025 as a critical point of concern for geologists and seismologists, particularly those based at Oregon State University. This undersea volcano, located approximately 300 miles off the Oregon coast, was once known for its predictability. Historically, it erupted in roughly 13-year intervals with minimal deviation and never posed a serious threat beyond scientific curiosity. That pattern, however, has now taken a potentially catastrophic turn. Recent data has revealed that the seafloor is rising at an unprecedented rate, with vertical movement reaching nearly 20 centimeters by March of this year. This uplift is not occurring in a uniform pattern, which is even more disconcerting because it suggests uneven magma intrusion. One portion of the volcano's summit is rising faster than the other, which could lead to tilted fault formations. This sort of asymmetry heightens the possibility of a sudden and violent rupture of the oceanic crust. One of the most concerning aspects of this development is the pressure buildup from within the magma chambers. Unlike the gradual, almost passive inflation seen in previous cycles, this current phase is marked by rapid acceleration. High-precision pressure sensors and satellite-based GPS arrays have confirmed that the caldera at the center of Axial Seamount is expanding in a balloon-like fashion. This expansion is creating internal tension that could exceed the strength of the crust above, increasing the likelihood of a fracture that would release magma explosively. If this occurs, it will not be a minor leak, but rather a forceful event with the capacity to cause significant geological disruption. Adding to these mounting fears is the detection of new and unfamiliar seismic activity. Unlike the typical tectonic tremors associated with fault line movement, these new signals have harmonic properties and occur in rhythmic pulses. Some of them resemble drum beats that last for extended periods, while others migrate outward from the central caldera, suggesting a propagation of stress and potential dike formation. These harmonic tremors are reminiscent of patterns observed before eruptions at other well-documented volcanoes, such as Kilauea in Hawaii and Bardarbunga in Iceland. The migration of these tremors has been mapped with remarkable accuracy, and the directional flow appears to be moving northwest, raising the possibility that magma is forcing its way laterally through the crust. Moreover, deep-sea sonar scans have unveiled a network of small cracks and fissures that align with the path of these tremors. These new fractures provide a structural map of potential weak points that magma may exploit as it continues to push outward. If a lateral dike eventually breaches the surface, it could result in a rapid and extensive eruption, potentially opening multiple vents across the ocean floor. This would not only release lava and gas, but also disrupt the seafloor's structural integrity. Compounding these concerns are continuous low-frequency vibrations known as harmonic tremors, which indicate the presence of pressurized gas or magma in confined underground spaces. These tremors are typically seen in the final stages before an eruption and have shown synchronization with elevated carbon dioxide levels in nearby hydrothermal vent plumes. One particularly eerie development is the detection of ultra-low frequency infrasound signals by ocean bottom hydrophones. These subaudible vibrations correspond to deep geological movements, possibly originating from the lower crust or even the mantle. Their presence indicates that the entire volcanic system is now operating on a deeper and more complex level than previously understood. The volcano is no longer just pushing upward, it is expanding its influence laterally and vertically in ways that defy past models. Researchers have described the phenomenon as the volcano breathing, with each tremor and seismic pulse acting as an exhalation that grows stronger and more pronounced with time. Simultaneously, hydrothermal vent systems at Axial Seamount have begun to exhibit disturbing changes. The temperature of vent fields has increased by 30 to 40 degrees Celsius in just a few short months, a drastic rise that suggests close proximity to magma. More alarming is the alteration in chemical composition of the vent emissions. There are now elevated levels of helium-3, a rare isotope that typically escapes only from deep within the Earth's mantle. This anomaly indicates that fresh magma, not simply recycled crustal melt, is making its way upward. The presence of helium-3 is often a harbinger of eruptive activity and is rarely observed unless magma is in the process of rapid ascent. Alongside these changes, marine life near the hydrothermal vents has begun behaving unusually. Tube worms and vent shrimp are migrating away from their typical habitats, a behavioral shift that has historically preceded vent collapses or underwater eruptions. These species seem to sense changes in their environment well before human instruments can, and their migration patterns provide another layer of evidence supporting the theory that a major geological event is on the horizon. To study this shift further, autonomous submersibles equipped with advanced mass spectrometry spectrometers and thermal probes have been deployed. These devices have confirmed increased levels of manganese and arsenic in the vent fluids, both indicators of magma-related rock dissolution. Even more concerning is the transformation in the chemical fingerprint of the vent plumes. This shift implies a change in the mixing zone between seawater and the magma-heated fluids, which could mean that the magma is now positioned closer to the ocean floor than ever before. Such a development would decrease the barrier between the molten rock and the surrounding seawater, thereby increasing the risk of a sudden and violent vent blowout. Events like this have been recorded in other oceanic ridges, where magma ascending rapidly fractured the overlying rock, resulting in abrupt hydrothermal collapses. These blowouts not only release immense amounts of heat and gas, but can also destabilize the seafloor, creating underwater landslides and localized tsunamis. Infrared imaging captured by submersible drones has added another dimension to the picture. These images show shimmering thermoclines, layers of water with different temperatures, surrounding the most active vents. These thermoclines appear to pulse rhythmically, possibly responding to pressure waves generated deep within the volcanic system. This rhythmic behavior has led to speculation that tidal forces may be interacting with magma chambers, causing cyclical surges in pressure and fluid movement. Compounding this, trace amounts of noble gases like xenon and krypton, elements that rarely reach the Earth's surface unless carried by rapidly ascending magma, have been found in the vent emissions. The detection of these rare gases suggests that deep mantle material is approaching the seafloor at an accelerated pace. The structural implications of all this geological activity are profound. Submersible drones have recently documented a network of new fissures radiating outward from the central ridge of axial seamount. Unlike the minor cracks seen in previous years, these are wide and long, sometimes spanning several kilometers. The formation of these fissures could be due to tectonic stretching, but the more plausible explanation is dike intrusion, where magma moves laterally through the crust and forces the rock apart. Should these dikes reach the surface, the eruption could occur without warning, releasing not only lava but also ash and toxic gas into the ocean. The violence of such an event would have far-reaching consequences, not just in geological terms, but also for marine ecosystems and coastal human populations. Geologists are now employing a suite of tools, ranging from sonar mapping and laser altimetry to high-resolution visual surveys, to construct a real-time model of how these fractures are evolving. Early simulations suggest that stress is accumulating in a fan-like pattern that radiates from the caldera and concentrates toward the northwest flank of the volcano. This section of axial seamount is composed of relatively young lava flows and is believed to be structurally weaker than other areas. As a result, it may be more susceptible to collapse under pressure. A flank collapse would not only reshape the local topography, but could also lead to significant underwater landslides. These landslides, in turn, would displace large volumes of seawater, potentially generating tsunamis that could threaten coastal towns and shipping routes. Another critical factor in this evolving situation is axial seamount's position relative to the Juan de Fuca tectonic plate. This plate is gradually sliding beneath the North American plate in a process known as subduction. It is one of the most volatile tectonic zones on the planet. If a major eruption at axial transfers seismic energy into this fault line, it could destabilize an already precarious boundary. This could conceivably trigger a larger, more devastating earthquake or tsunami affecting the entire Pacific Northwest. What began as a local phenomenon beneath the ocean floor could therefore catalyze a broader chain reaction, implicating not just the geological integrity of the seamount itself, but also the stability of the surrounding region. As the scientific community continues to analyze these changes, there is growing consensus that axial seamount is no longer a passive geological feature. It has transitioned into an active and volatile system capable of producing effects that extend far beyond its immediate surroundings. The intricate interplay between magma movement, tectonic stress, chemical changes, and biological responses forms a complex and dynamic narrative that challenges existing models of undersea volcanic behavior. Instruments that once recorded gradual changes are now picking up signals that suggest a system in overdrive, with pressure increasing across multiple dimensions and at multiple depths. In addition to physical changes, the ongoing research effort surrounding axial seamount is pushing technological boundaries. New generations of underwater drones, seismic sensors, and chemical analyzers are being tested and refined in real time, offering unprecedented insight into one of Earth's least accessible environments. These tools are not only helping scientists understand axial seamount, but also providing templates for monitoring other potentially dangerous undersea volcanoes around the globe. The data collected from this site may therefore serve as a cornerstone for future geoscientific studies, enabling better prediction models and more effective early warning systems for both natural disasters and ecological shifts. The urgency of this research cannot be overstated. created. While much of the activity remains beneath the surface and invisible to the naked eye, the signals are growing stronger and more coherent. From seismic swarms and vent anomalies to expanding fractures and rare gas emissions, the evidence all points in one direction. Something unprecedented may be unfolding beneath the Pacific Ocean. It is a geological story still being written, with each new data point adding a layer of complexity and concern. What was once considered a predictable feature has now become a potential catalyst for large-scale environmental transformation. Understanding the full implications of axial seamount's awakening will require continued vigilance, interdisciplinary collaboration, and a willingness to challenge conventional thinking. The sheer number of variables involved, from tectonic mechanics and fluid dynamics to gas chemistry and ecological response, demands a holistic approach. As scientists work tirelessly to interpret the signals, they are racing not just against time, but against the limitations of current knowledge. For now, the volcano remains silent, its rumblings confined to the depths. But if current trends continue, that silence may soon be broken in a way that reshapes both our scientific understanding and the physical world around us.